Suppose you have a rocket. The mass of the rocket is m, and the mass of the fuel is little m. So the total mass is m plus little m. When the rocket shoots out the fuel as exhaust, the fuel has a constant exhaust velocity of Vex as measured with respect to the rocket. If your only goal is to achieve the highest final rocket velocity, would it be better to release all the fuel at once, or would it be better to use the fuel at a lower rate and fire the rockets for a longer time? So what we're going to do is we're going to test this out in Kerbal Space Program, which is a game, or it's really more of a simulation. It's a rocket simulation. And the physics, it has a pretty decent physics engine, and it's pretty cool. So what I did was I made a couple of rockets and I tested them out to see which situation is better to achieve a higher final velocity. So these rockets both have 4 engines. Now the one on the right launches with 2 rockets, and then when those 2 run out of fuel, it engages the other 2 rockets. And the one on the left launches with all 4 rockets. And the one on the left, as you can see, ends with a higher final velocity. The next couple trials, I turned off gravity and air resistance, and instead of having actual thrusters, I attached masses to the rocket. And the 2 on the left detach two masses, and then later they detach another 2 masses, whereas the ones on the right detach all 4 masses at once. And as you can see, the ones that detach all 4 masses at once have a higher final velocity. Now for this one, well, for these 2 I did the same thing but with 8 masses, and you can see the one on the left detaches 2 at a time, and the one on the right detaches all 8 at once. And the one that detaches all 8 at once has the higher final velocity. So from these tests, at least, we can say that the final velocity, the higher final velocity of a rocket is achieved when you launch all the fuel at once rather than releasing it at a lower rate for a longer time. And so if we look at the rocket equation, which this is showing the derivation of it, where you start off with Newton's second law of motion equation, and you move some stuff around, do the derivative, and you end up with delta V equals V external times the natural log of the initial mass over the final mass. And so I guess we'd want to see if the rockets in this game actually follow the rocket equation. The first thing we're going to need to find is V external, which we can do by multiplying the specific impulse times the gravity. And the specific impulse for this thruster is 280 seconds. If we find the average specific impulse for all 4, we can do that using this equation, and we find that this 4 times 200 on the top and bottom cancel, and you get 1 over 280, so you get 280 seconds, which was the specific impulse. And from that you can see that if you have 2 or if you have 4 engines, the specific impulse will still be 280 seconds. And then we multiply that times 9.8 and find that Vx is 2,744 meters per second. So if we multiply that times the natural log of our initial mass was 17.8 tons, and our final mass with no fuel in it is 8.5. So if we multiply that together, we get 2,280 meters per second. Now, this is much more, it's 1,000 meters per second more than the final velocity that we got for all 4 rockets. But this equation doesn't take into account air resistance or gravity. So I ran the simulation again without gravity and air resistance and got 1,734 meters per second as my final velocity. And I couldn't run the thrusters at full velocity, at max velocity, because the rocket kept exploding. So I think if the rocket would have ran at full velocity instead of I had to run it a little bit less than half so the rocket wouldn't explode, I think it would have gotten to 2,028 meters per second. I feel pretty confident, though, in saying that to achieve a higher final velocity, it'd be better to release all the fuel at once than to release the fuel at a lower rate and fire the rockets for a longer time.